Hello, good day. Welcome back. I'm sure you are revising everything that you've been taught so far. If not, please go back and start revising so that you would be able to continue to learn and move along with this course. Today is day 22. You're going to learn about PWM. This is the sections we are covering today. You're going to learn what is a PWM and how that is to be used in your programming and how you can use it in your application. And also you will start to learn to program from line 1 to generate some sort of duty cycle percentage using a timer that you will learn. Before jumping in, I would like to introduce myself. I'm representing A2DG. It's a startup by Anbukarasu Brothers, by Alex, my brother, and myself, Arul, in 2023. Both of us gathered 20 plus years industry experience, and we would really like to put it out there to help you all to shape you into a better professional. And our mission is to convey to at least 100,000 future professionals through our online courses. And that's one of our main advantage, that you can study at your own pace wherever you are. That's really good. A little bit about me. I am Arul P. Bukarasu. You can call me as Arul or API, as persistent as I would like to be, to share my knowledge and my experience with you all. I have 20 plus years working in various industries in various countries, in Australia, Italy, Singapore, and India. All my expertise on the renewable energy sector, on solar and wind, power systems, lead acid batteries, network embedded systems that's connected to ATMs, TCRs, and POS, banking automation systems, and smart parking operations. My expertise lies on these three: embedded systems, VLSI, and project management. A small announcement to make. I categorized into two different categories: the YouTube viewers and the internship professionals. All the videos that been recorded will be displayed and put in YouTube channel under A2DG. In order to be eligible to get a free certificate, you got to attend at least 28 videos, and at the end of each and every session you will have an attendance link, so please fill that out and send it across to me, and that will help for your attendance. And due to YouTube regulations, videos can't live there forever, so in case if you missed a session, if you want to go back, unfortunately you can't do the recap. That's why I strongly recommend you and advise you, please join our internship program. That would acquire you to get an internship certificate, and that's worth a lot in the industry. When you land into the interview or got your first job and working with the senior engineers, they will see this 30 days that you put your hard work on to learn all the basics, the fundamentals, and also the project that you already have your hands on counts a lot. And also you will have your own login details, so you can log into our learning management system portal and you can go through each and every session. And once you finish a session, when you click on the complete button, that will count as your attendance. Not only that, you will get unlimited access to all our course contents, all our PDF materials, the source codes, the reference manual, the data sheet, and other schematics, etc., whatever you need in this program. And also the number of course videos, it's unlimited for you. You can pause, you can go and do something and come back. If you want to go back, you can do that. It's all yours to keep. In case if you get stuck in that, please contact our backend support team and they would be able to assist you to make you move along in your learning curve. So can we get in to learn about it? I'm sure you are keen as I am, so let's get in to learn what's out there. PWM. What is PWM? As you know by now, PWM is pulse width modulation. It's a way to control analog signals from digital devices. As you know, analog signals comes in continuous pulses, so you need to capture that and you need to analyze that to control something. So the pulse width modulation, it's mainly used to control something. For example, if you want to control the brightness of a globe or a bulb or a LED, you can do so by using the pulse width modulation technique, and you can brighten the LED or you can dim the LED, brighten the LED like that. And also you can, with the PWM, you can also control the speed of the motor. You can slowly degrade it and you can rev it up and make it go faster. So that's where pulse width modulation comes in. In any waveform, you would realize you would have a high period and a low period. So the high section is called the on time, and the off section it's called the off time. The total duration of on time and off time is the period in any waveform. So that's where the pulse width modulation is related to. So whatever time the wave stays on the on time, that's called the duty cycle, which you will learn in the next slide. So this graph is considered with 0% duty cycle, so there is no current flowing through. So therefore, if you want to control an LED, the LED won't glow or blink. With 25% duty cycle, that means the current flow will be on the circuit 25% of the time. So that means if you take a scale of 0 volts to 5 volts, to convert that to 25%, which is about 1 volt. So you need at least 3 volt for a LED to operate. That's the difference between the duty cycle, and this is the 50% duty cycle, meaning on 50, off 50, on 50, off 50, and this is 70% duration, so 75% on the time, 75 off the time, and this is the 100% duty cycle. In this case, the LED will stay as glowing, it won't go off. I got a small video clip to introduce to you, so this would make you understand and learn more about the pulse width modulation. So please take plenty of notes and listen to this video and follow this.
Or PWM. Pulse width modulation has many different uses because it allows us to finely control different electronic devices. In this case, I'm pulse width modulating an LED, which means that I'm pulsing the power supply on and off at a certain frequency and with a certain pulse width. Pulse width modulation allows us to control the brightness of lighting, whether that's a standard bulb or LEDs, or it allows us to control the speed of motors. Pulse width modulation also allows us to make very efficient power supplies such as step up, step down and regulated power supplies, all known as switch mode power supplies. The switch mode in the name refers to the pulse width modulation technique. Now bear in mind that every circuit doesn't run fast enough for me to show you what the LED would do, but in this case the LED would actually dim and brighten depending on the pulse width that I'm sending to the LED. So let's just have a look at the power supply which I am applying a pulse width to. In this case, in every circuit, it's shown in a much simpler form. This would actually usually be some sort of microcontroller that is sending pulses at a certain frequency and at a certain width, turning a power supply on and off. So when this power supply is turned on, it's sending current through to this LED. And when it's turned on, its voltage when it's high or on is 3 volts. And when it's low, also known as off, it's 0 volts. So for every on pulse, there is 3 volts and 20 milliamps going through this LED. And for every off or low pulse, there is no current flowing through the circuit. In this case, it's pulsing every 1 millisecond, with a pulse width of 50%. The pulse width of 50% means that current is flowing through the circuit 50% of the time, and current is not flowing through the circuit 50% of the time. So the on time is equal to the off time. If I increase the pulse width to 80%, you can see the result on the graph at the top. Current flowing through the circuit is now on more of the time versus the off time. So the current flowing through the circuit is flowing 80% of the time during the pulse width, and no current flows through the circuit for only 20% of the time. If I further increase the pulse width to 100%, you can see what's happened. Because the pulse width is 100%, current is flowing through the circuit 100% of the time. So there is now no point in time where the circuit is turned off. If I decrease the pulse width to 10%, you can see that the circuit is off most of the time, and only pulses on very quickly, 10% of the time. If I change the pulse width to 0%, you can see that the circuit remains off all of the time. The other thing to look at here is the frequency at which we're pulsing this circuit. Currently, we're pulsing it at 1 kHz. If I increase the frequency of these pulses, you can see that the pulses get much faster and appear shorter on the graph, although this is still 50% pulse width modulation. It's on 50% of the time and off 50% of the time. But now the frequency has gone from 1 kHz all the way to 10 kHz. And this means that we are pulsing this circuit 10,000 times per second. I can also slow it down by decreasing the frequency. You can now see that the frequency is 502 Hz, which means that this would be pulsing 502 times per second. In this case, when we're pulse widthing an LED, if we pulse it too slow, we would be able to see the visible pulses, which would not be ideal. So let's go on to a visual example of pulse width modulation using
I'm sure you were able to capture all of that, so let's continue further.
or PW.
Next is the duty cycle. What is the duty cycle? The duty cycle is a way to control the power given to any analog device in terms of pulse width modulation. In other words, the term duty cycle refers to how much time the pulsar stays on the output that spends on the on time, that's on the high time. As you can see here with the graph, this is shown on a 50% duty cycle, which means 50% on and 50% off. And this is shown with a duty cycle with 70% on and 30% off. Also, this varies with 3 different duty cycles with 10%, with 50% and 90% on. So this is about the duty cycle. We're going to use timer 2 in our program, so let's know a little bit more about timer. A timer sometimes can be referred to as, you hear, as a counter as well. It is a special piece of hardware that sits inside the microcontroller, and in many microcontrollers we do have in STM32 as well. We're going to use timer 2 in this example. Their function is simply either to count up or count down as per the configuration. By default, this timer counter will be set as an up counter. If you want to do the down counting, then you need to change the configuration, and that will change to down counter. So for example, in an 8-bit count, it will start to count from 0 to 255 and it will keep rolling over, meaning when it reaches to 255, it will reset and it will start again from 0 and go till 255, and the cycle continues. So that's how the timer works. And the main application where the timer is used is mainly used in generating a delay. So when we write a program, when we use a delay, we give a time period in that delay. So that is nothing but that's coming from a timer. So that's where the timer is really very useful in any application. Some of the areas where other areas where the timer is mostly used is to update any events and to count those events and creating delays, measuring time between first event and the other event. So this is where all the timers used. When you compare with timer with the counter, timer is an internal clock source, whereas counter is an external clock source. For example, the internal clock source can be a phase lock loop PLL, and it has its own crystal XTEL. So that is the timer because it lives inside the microcontroller, so therefore it doesn't need any external clock source, whereas the counter can be from an external clock source, so you can feed to a CPU. So that's the basic difference between a timer and a counter. In STM32 timers, these can be used as the base generator and can be worked upon 3 different modes. The input capture mode can measure the frequency of an external event. The output compare mode controls the output waveform, and if the period elapses, then that compares with the input capture mode. So that's what the output compare mode do. Also, there is a third one called one pulse mode. One pulse mode is a counter that started in response to, if you generate a stimulus to it, it generates a pulse, and that turns out to be a programmable delay. Depends on the pulse how long it stays. So these are all different timers that you could use in your project. And as you know, in microcontroller we always have to work with the registers and so forth. The timers also has its own registers. So these are all the three main registers you will be writing your program on. First is the timer count register. This is the register which shows the current value of the counter. The size can be 32-bit or 16-bit, and our program is based on a 16-bit counter. And the second one is the timer auto reload register ARR. So this is used to set for a flag. When the timer reaches the count, it raises a flag knowing the count is there, and then it will reset it and starts to reload and start the count again. So that's where timer auto reload register is used. Then the third one is the timer prescaler register. As you know, the purpose of the pulse width modulation, the timer, is to control the intensity or control some fastness to it. So that's where the prescaler register comes in handy. So the prescaler register will do the speed reduction, and it slows down the processing speed. So it will divide the timer by the input clock of the timer. So if the input clock is, for example, we are using 16 megahertz, to get to count to 16-bit, it will further reduce its clock. So that's where the prescale register is used. This is one good example. The system clock comes out here is a 16 megahertz. It sends to the advanced high peripheral bus, and the advanced high peripheral bus, the clock is again divided up to by 512. So 16 megahertz will be divided by 512, and that clock is further sent to the H clock, which will be further divided to slow down its process, and it can divide down to 256, and this split to the peripheral buses APB1 and APB2, and this is where we set the bit counter, how many bits we're going to use. So this can count to 16 bits, so this will be divided, whatever this clock coming here will be divided up to 16, divided by 16, and that's sent to as a timer as a prescaler. So the prescaler can start to count from 0 to 65535, and this is how the counter is used for the application. So this is really one good example. Another example, as you can see, there is the high speed external and the high speed internal connects to both the phase lock loop sensor, and this one connects to a mux with a system clock coming through 16 megahertz. That's the mux coming out, and in this example it's divided by 2, so you get the same H clock as 16. Because we're using a 16-bit, we need the output as 16, so that's why the dividing factor is 1. Again, you branch that out to APB1 and APB2, and this is how you connect to your application. Application meaning, in this example, you're going to control the intensity of the LED. You can also send the 16 count to control the motor speed. So like that, this is how the prescaling is done. And these are all the terminologies that's associated with timer. First is the update event. When timeout occurs on how long it takes for a flag to be raised, that's called an update event. When there is a flag raised, when any timeout happens, that's considered as an update event. The period is the value that's loaded into the ARR register, that's called a period. And then the up counter, as you know by the word, starts to count from 0 to the top value. And the down counter also, you know, it starts to count down from the top value to 0. So these are all some terminologies. Also, you can do so by calculating your own update event by using this formula, and you can understand. For example, this one I given as an example with 48 megahertz. So if you calculate that with 16 megahertz for our program, then you can get the desired output. So the update event, timer clock divided by prescaler plus 1 times period plus 1. So the prescaler should be adding with 1, and period also be adding by 1. As you know, the time is 1 divided by frequency, so t is 1 by frequency, so you get 0.5 seconds. So this is how the time computing update event is calculated. And also further, if you want to know about the timer clock, this can be calculated by these formulas. The timer clock is advanced peripheral burst timer clock divided by the prescaler value, and the frequency can be calculated by the timer clock divided by the auto reload register. And the duty percentage can be calculated by the capture compare register divided by the auto reload register times 100. You get the duty percentage that way. And these are all the registers that you will be using in the program. First is the prescaler. This is the prescaler value, and this is how you're going to declare it. Timer to prescaler value, you're setting the value to 1600. So every time you need to count with -1. Then the auto reload register, you need to set a prescaler value to 1600. So if you do the calculations, you will get as 10,000. So this is how you need to load. The control register is used to enable or disable the timers. To enable timer 2, you need to use control register 1, and set as 1. That means it will enable the timer. And the status register is to check for the flags and set the flag and reset the flag. To check the update, you just simply AND with the status register. To clear the flag, you need to AND and negate with that status register to the timer. This is the capture compare register. So one capture compare register for each of the 4 channels. So there are 4 channels used. So in our example, we will be using CCR1. So this is how to read the captured value. And also there is capture compare mode register, CCRMR1. This is used for configuring either the capture or the compare functionality, and they have 4 different channels. To use CCMR1, that is to set channel 1 to capture at every edge, you need to write this 0x41, and you can use, and I connected the logic analyzer as well, so you can use the channel 1. If you want to use channel 1, that's the value. For other channels, you need to accordingly calculate and get a value and use that in CCMR1. The control register 2, sometimes it's used for the enabling and disabling the ADC, and also it is used for enabling the channel. So you need to set the CR2 to 1 to enable channel. Okay, I'm sure you got all the theoretical bits. Please, I'll give you a couple of minutes break. You go and have that break. When you come back, I will show you line by line about how to write this code, and you will verify that in Pulse View using the logic viewer, and raw logic analyzer. You will verify the output. So go and enjoy that break. I'll see you in a couple of minutes. See you then.